Well, good morning. I'm sorry it's 11 minutes late getting started, but I had students stop by and ask questions and talk about coronavirus and all sorts of things at the end of my last class, so I didn't get to run down to my office and exchange books till just a few minutes ago. So sorry I'm late, but nobody's here, so we'll go on and get started. This is 11:41 on Thursday, the 12th of March, 2020. It's supposed to be linear algebra class, and like I said, I'm the only one in the room. So let's proceed from there. We finished chapter 2 last time. That was matrices. We're starting chapter 3 this time, which is the shortest and perhaps the easiest chapter we have in the whole text. And this will be is chapter 3 on determinants. Now, the first part of it, the very first part, is pretty easy, okay? After a while, they try to muck it up some by making some fairly complicated definitions and things, but in reality, doing determinants are usually not that awfully bad. Of course, you get a huge size matrix, yeah, it becomes pretty tough to do anything with it, including determinants. So let's go from the current slide. And why it's not going to the current slide, I don't know. Here we go. All right. Now, first part I think we actually have already done. If not, we come awfully close to it. Now, here's a key concept here. Every square matrix can be associated with a real number called its determinant. Every square matrix. If it's not a square matrix, you don't even try doing a determinant, because you can't do a determinant on a rectangular matrix unless it happens also to be a square matrix, okay? So, historically, the use of determinants arose from the recognition of special patterns that occur in the systems of linear equations, and I'm going to go through this. This is sort of a ugly slugging through things, but it is true and it works. What if you have a general two-system equation, system of two equations and two unknowns? One reason I'm pausing here is my computer, after it gets hot, it has trouble charging. So I have to twist my cord to make it connect better. But I think I've got it better now. I can't guarantee it'll stay this way. So let's get a very generic expression of a two-by-two system. A sub 1, 1, x1 plus a sub 1, 2, x2 is equal to b1. A sub 2, 1, x1 plus a sub 2, 2, x2 is equal to b2. Simple a system of two equations, two unknowns. Okay? Now, don't know if you remember how to do this, and whether you do or not, well, I'm going to do it for you. How you solve a system of two equations, two unknowns. There's several ways. You could graph them. Of course, we don't have any numbers in this one. That would be really hard to graph. Since we don't know what these coefficients are, it would be hard to do solve by substitution. You could, but it would be messy. So the simplest thing is what they called elimination by addition. Okay? And what we're going to do here, we're going to eliminate the x2 variable, and how we're going to do that is multiply the top equation by a minus a12, I think is how they're doing it. Minus a12, and that would be multiplying the bottom equation. No, I'm sorry. Bottom equation by minus a12, and the top equation by a positive A22. Okay. Now, in other words, multiply this, if we're eliminating the x2, multiply the top equation by an A22 and the bottom equation by A12. In other words, you flip the coefficients, make one of them negative, and what you have then is A11, A22, x1 plus A12, A22, x2 equal A22, B1. Second equation, you have a minus A12, A21, x1 minus A12, A22, x2 equal minus A12, B1. Okay? Now, here's what you accomplish by doing that. Notice these two terms are identically the same but opposite sign. They add to be zero. That's why I call it elimination by addition. So that gives us, I'm going to skip maybe a little step here. Your x1 coefficients, when you add these two together, is A11, A22 minus A12, A21 times x1 is equal to, this is a B2 here, I don't know how it became a 1, A22 B1 minus A12 B2. Okay? Then divide both sides by this expression here. Goes out here, and this would then be A11 A22 minus A12 A21. Okay, so that's your x1, and you'll see that is exactly, now they wrote the b's before the a's in the numerator, that's okay, and the denominators are identical, except they wrote the A21 before they wrote the A12. That's okay. A similar way you could solve for x2, and this is your x1 here, okay? Your x2 would become, I won't work it out, but you could do the same type thing. I'll get you started on it if you want to prove it to yourself. This time, multiply the top equation by I think a minus A21 and the bottom equation by a positive A11. Okay, and when you do that, you see the first entry here would be a minus A11, A21. First entry here would be a positive A11, A21. So those terms are going to go to zero, add to zero, and then you'll get what you're doing there, and your x2 would come out being B2 A11 minus B1 A21. Okay, and your denominator would be A11 A22 minus A12 A21. Okay. Now, those are your solutions for that system. Now, things to notice here. They have the same denominator, don't they? Okay, even though you did different processes, they wound up with the same denominator. Okay, and what is that denominator? Well, you see it right there. But what I'm going to do is go back to my original thing here and write this as a matrix. A11, A12, A21, A22 times x1, x2, we've done this many times before, is equal to b1, b2. Okay? Now, let's look at that denominator and see what it is. A11 times A22 minus A12, A21. Look at that. What is that? That is what we define as the determinant of the coefficient matrix. The positive product of your down diagonal, main diagonal, A11 minus A22, times A22, minus the up diagonal, your other diagonal, the product there, minus A12, A21. That is your determinant of the coefficient matrix. And that's the denominator of these. Now, a little bit later, we're going to do the numerators as well. Okay? But right now, we're just going to stick with the denominators. Okay? Now, that expression here is called, goodness gracious, this is aggravating. It's where this matrix is matrix A. This expression then, made up of that matrix A, is called the determinant, and you can write it out as det of A. Okay? But the easier way to write it, and the way I usually do, is this one. It looks like absolute value of A, but you don't take absolute values of matrices, take absolute values of numbers. But it's the same symbol, two vertical lines there, that means determinant of A. Okay? Now this, of course, A is just a 2 by 2, so it's a pretty simple thing. If it's a 3 by 3, you have 8 terms in it, I believe. A 4 by 4 would have 16, 32, I mean, the number of terms just explodes. So it is a pretty simple concept, but it has, it can get complicated pretty quickly. So let's do example 1, which is merely finding the determinant of a bunch of 2 by 2 matrices. A pretty easy thing to do. Okay, here, the A part here, for A is 2, negative 3, 1, 2. Okay, what is the determinant of A? That'd be 2 times 2 is 4, minus a minus 3, so it'd be plus 3. That's equal to 7. Okay? Here's a matrix B. 2, 1, 4, 2. Determinant of B would be down diagonal 4 minus the up diagonal minus 4. That one's 0. Huh, that's interesting, huh? And here's matrix C. 0, 3 halves, 2, 4. Determinant of that matrix C is 0 minus 3. It should be a negative 3. Okay? Now, things to note here. determinants may be positive, they may be negative, they may be zero, they may be fractions. We didn't have one that was fraction, but it could easily be. They could be rational, they could be irrational, they could be any real number. Most of the time, most of our determinants, hopefully, will be integers, okay? Not always. Just throw a few fractional terms in there or decimal terms, you're almost certainly going to wind up with a decimal determinant. But most of the time, we've been dealing with matrices made up mostly of integers, and if they are, usually the determinants come out being integers. But they could be positive, could be negative, and they could be zero. Now, the positive and negative don't really matter that much, but if a determinant is zero, that says something about that matrix, okay? And if you look at B, whose determinant is zero, you might see what that might be. In a 2 by 2, they're really easy to pick out because one row is always a multiple of the other row, okay? In other words, this is a dependent system, okay? You do not have, these are not independent of each other, they are dependent. One row is a multiple of the other row, okay? Now, that's jumping ahead, so you can ignore that if you want to. Now they're going to talk about how to do bigger matrices, like going into 3 by 3s, okay? And they do this by a couple of new terms here, and the terms themselves are really wordy, okay? The concept is not that bad. The terms can be a little wordy. So to define the determinant of a square matrix, remember you cannot take the determinant of an unsquare matrix, okay? It's got to be a square matrix. And if it is a square matrix, it's going to have a determinant. It'll either be positive, negative, or zero. And really the positive and negative don't matter that much. The zero does matter, okay? And we'll get back to that later, okay? But if you are doing anything higher than 2 by 2s, then it's convenient to use, they say convenient, to use minors and cofactors. So here's what our definitions are. A, of course, has to be a square matrix. Has to be, okay? Then the minor, which we call M sub ij, okay? Now they didn't tell you what A was, just a square matrix, but we're using the i's and j's just like we did before. I is related to rows and j is related to columns, okay? But the minor Mij of the entry Aij. Now I know exactly what that is. That's the entry that's in the ith row and the jth column of matrix A. So what is the minor of that entry? It's the determinant okay, the determinant of the matrix obtained by, this is really a little awkward, deleting the ith row and jth column, okay, of the matrix A. Okay, now we'll get back to this later. The cofactor Cij, they capitalize both of these, of the entry Aij is merely minus 1, this looks so confusing, it's not bad, of I plus j times the minor of ij. Okay, now remember, the minor is a determinant. It's the determinant of a smaller matrix. The smaller matrix you come by eliminating the ith row and the jth column of A. So if A was a 7 by 7, then the minor of the fourth, fifth entry, I sub 4, 5. You eliminate the fourth row, the fifth column, and then you have a 6 by 6 matrix left. The determinant of that matrix is the minor of 4, 5. Minor 4, 5. Okay, it's a 6 by 6 matrix. Okay, the cofactor is whatever that determinant is multiplied either by plus 1 or minus 1. Because you see, minus 1 raised to, if I, the example I just gave, 4 and 5, 4 and 5 are 9, that's an odd number, minus 1 to an odd power is a minus 1. If that had been the third and fifth entry, then that would have been an even power, and minus 1 to an even power is a plus 1. So your cofactor is merely your, whatever that determinant of your, that remains when you eliminate those rows, the determinant of that minor is either going to be plus or minus of that. Okay? And you determine the sign of the plus or minus by the position of that ij entry. Now, they didn't quite say it that way, but that's indeed what it is. Okay? And they do give an example here that I will try to follow. Okay? I think I'll go on and erase just in case I need more room. Okay, I don't think I will, but just in case. Okay. Here's your matrix. A11, A12, A13. A21, A22, A23. B31, B32. Where did I get a B? Goodness gracious. Okay. A31, A32, A33. That's your matrix A. Okay? Now your minor, your 2, 1 minor of this matrix A, we'll call it, is eliminate the second row and the first column. And you have a 2 by 2 left. It was a 3 by 3, now it's a 2 by 2. And take the determinant of that, that would be A12, A33 minus A32, A13. You could write that as A13. A32 if you wanted to. It doesn't matter. That's what you got. That determinant of what's left. Okay? Now, that's all that the minor is. Okay? Now, the cofactor 2, 1 of that same entry there, 2, 1, A21, is either plus or minus times this. Well, let's see what the I is. The I is 2, the J is 1, 2 plus 1 is 3. Minus 1 to the third power is a negative number. So that would be the minus of M21. You just multiply it by either plus or minus 1, depending on whether the sum of the subscripts is positive or negative. If they're positive, you multiply by a plus 1. I'm sorry. If they're an even number, multiply by a plus 1. If the sum of those two is odd, which this it is, you multiply by a minus 1. Now the m itself could have been a minus number, but if it is, then you negate it and it becomes a positive number. Okay? Now same one, so I'm going to, what I'm going to do here is, being very lazy, is erase as much as I can of what I drew in there. Okay. Oh, I think I got most of it. Okay. Now the next one we were going to do is the minor of and cofactor of A22. Well, A22 sits right there in the middle, so we eliminate the second row and second column. And the minor of 22, the 22 entry there, would be A11, A33, minus the up diagonal would be A31, A13. Okay? That is the minor of the A22 entry. Okay? The cofactor of that 22 entry would just be the same as the minor of the 22 entry, because 2 plus 2 is 4. 4 is an even number. Negative 1 to an even power is positive, so that would just be the same as M22. Okay. So, it almost sounds a little complicated or convoluted. It really isn't, not in practice. They're pretty easy things to do. I think I'll leave that. I was going to erase, but I think I'll leave it. But here's something to note, okay? When you're doing that cofactor, what sign do you use? You can add the subscripts together. If it's even, it's a +1. If it's odd, it's a -1, okay? Or, if you don't want to do that, here's another thing, and they show you this. I think I'll just write this down. I'll do the 3 by 3 we did, except here, I'm not writing entries in. I'm just showing you what your sign of your cofactor will be. Okay? Plus, minus, plus, minus, plus, minus, plus, minus, plus. Any way you go, you alternate signs every time. Now, you only go right, left, up, and down. Okay? So if you started here, plus, minus, plus, minus, plus, minus, plus, minus, plus. Started here, plus, minus, plus, minus, plus, minus, plus, minus, plus. Started here, plus, minus, plus, minus, plus, minus, plus, minus, plus. Any way you go, you always go out the same way. That's a 3 by 3, a 4 by 4. I'm going to be very lazy here and just expand it this way. Okay, there's a 4 by 4. The pattern stays the same. Plus, minus, 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 plus, minus. Anywhere you start, minus, plus, minus, plus, minus, plus, minus, plus, minus, plus. Right, left, back and forth. Now, it doesn't say anything about diagonals, okay? Except everything on the diagonal is, the main diagonal is always plus, okay? That's the only thing you can always say. But you don't go diagonally, because diagonally you have same signs. So you don't go that way. You only go up and down, right and left, and then you always have the opposite sign next to you, okay? And you go on and on and on. They just get bigger, but the sign pattern stays the same. Okay. So, this next example, frankly to me, is a real big pain in the neck, okay? But we can do it, okay? Here is A. A is a 3 by 3 matrix. 0, 2, 1, 3, -1, 2, 401. Okay. Find all the minors and cofactors of this matrix. Okay. So let's do the minors first. M11. Okay. Now, I'm going to gently wipe out the first row, first column. The minor is the determinant that's left. That's a -1, -0, that's -1. Okay? Now, we'll do M12 next. Okay, M12. I don't know where my pen is, but it's not showing up. Well, my whole computer shut down. Not really, but close. There we go. Now I can't. Okay. This is so aggravating. I don't know why it does this. I think it has something to do with that power cord getting hot, the connection getting hot, and not making good contact. I don't know what's happening. Okay. Yeah. So M12, we're just going to leave the first row out, but eliminate the second column, and that determinant is 3 minus 6 is a -3. Okay. Then the M13 entry, or minor, is going to be, wipe out the third row, and you get 0 plus 4. That's going to be a +4. M21, okay, I'll wipe out everything we just did, that one and that one, and wipe out second row, first column. Okay, so M21 would be 2 minus 0 would be 2. M22 would be, we'll erase the first column there, keep the second row wiped, and erase the, and wipe out the second column. That would be a 0 minus 4. Okay? After a while, you don't need to wipe them out. I'm going to keep doing it just so you get used to it. The M23 entry would be wiping out second row, which we already wiped, and the third column, and then you get 0 minus 8. Okay. Now move to 3-1. 3-1 minor. Wipe out third row, first column. Take the determinant with what's left. You get a 4 minus a minus, which is +1. That's a 5. Okay. M32. Keep wiped out the third row. I can't get my pen back. Sorry. Woo. Wipe out the second column. As I think I've told you before, at some point, I'm hoping it's mostly just because my red cell count is so low, my hemoglobin low, my hematocrit's low, I just get so tired and so easily, and it's pretty late for lunchtime too, so there's that also. So I did grab me a little snack when I went down to the office, but it's worn off pretty much now. Okay, but I'm sorry, I'm just really tired. Okay, wipe out the third row, second column, and take the determinant of what's left, 0 minus 3. So that's a negative 3. All right, and then finally the M33, the minor for the 3-3 entry, A33, would be wipe out that bar and put in 3-3. 0 minus 6. Okay, those are all your minors for that matrix. Okay, now the cofactors are exactly those same numbers, but possibly with different signs. Okay, and rather than do the i's and the j's, let's just do them the way I said before. So I'm just going to write down, C11, C12, C13, C21, C22, C23, C31, C32, and C33. Put equal signs after every one of those. Okay, now, what I want to remind you, plus, minus, plus. Plus, so that's going to be a minus 1. You don't change the sign to a plus, you do the positive of that number. And the positive of minus 1 is a minus 1. The negative of a minus 3 is a 3. The positive of a 4 is a 4. The plus minus a 2 is negative 2. The positive of negative 4 is negative 4. And the minus of negative 8 would be 8. Okay? The plus of 5 would be 5. The minus of negative 3 would be 3. And the positive of negative 6 would be negative 6. Okay? So that's all you do. It's just adjusting signs. Minus 1. Now, how did I must have done a math error. Wait, let me back off. This one right here, and this one right here. I must have messed up on 1, 2. 1, 2. 3 minus 8 is negative 5. And the opposite of that would be 5. Okay. Yeah. Okay. So negative 1, 5, 4. Negative 2, negative 4, 8. 5, 3, negative 6. Okay. The cofactors are just either plus or minus of the minor. And you just have to determine which by the position. Okay? Now, they don't really call it position much. That's how I think of it. Now, that wasn't bad. Wasn't too bad at all. This next thing is absolutely true. It just seems like to me it's getting a little more complicated seeming. Now, the definition below is inductive because it uses the determinant of a square matrix of order n minus 1 to define the determinant of a square matrix of order n. Okay? It's kind of what we've just been doing. Okay? If A is a square matrix of order greater than or equal to 2, 2 by 2, 3 by 3, 4 by 4, anything like that, then the determinant of A is the sum of the entries of the first row of A multiplied by their respective cofactors. Okay? Row. That is, okay, let me clear the screen so I can write that, because I don't know if all of you, both of you have books. I know, I think Dawson has an e-book. I don't know about Josh. Oh, my goodness, I'm running out of steam. And the other thing is I forgot to bring up, I didn't know no student would be here, so I didn't bring up time device. And since I need to get something like a little caffeine or something, let me pause right here and I'll be right back with my... All right, sorry about that. It's 12:25. I had not brought a watch in. My watch band broke and the battery died. Everything happened to it, and I haven't been able to get that repaired yet. But sorry. Also brought in a Coke because I need something to keep running. Part of this probably is the anemia, but part of it is also the fact that this week we've been doing fall schedules. The summer schedule was due last Friday and fall schedule was due yesterday. So they gave us 3 days to do the worst schedule of the year. And I was here until 7:30, 8 o'clock, maybe even later on Monday night. I was here till almost 9 o'clock on Tuesday night. I was over on the Birmingham East Campus until 7:30 or 8 o'clock last night, finishing up because I have so few office hours during the day. And as Dawson and Josh may know, I even missed some classes yesterday because I had to get the schedule finished. So sorry, but I've just been running so ragged that part of it is just probably exhaustion, but the other part I think has to be the low red cells. So sorry too much about that. So let me write down what I was just saying. Okay. If a square matrix, of course, okay, of order, and this is almost ridiculous, n greater than or equal to 2. Guess what? A 1 by 1 matrix we're not going to fiddle with, okay? But anything bigger, a 2 by 2, 3 by 3, 4 by 4, whatever, 17 by 17, whatever, any order greater than or equal to 2, okay. If that's the case, then the determinant of A, I should have just run absolute value bars, is the sum, okay, of the entries of, now, here I really even don't want to write this down. They say the entries in the first row of A. Okay, multiplied by their respective cofactors. Okay, so here's the other way of saying it. The determinant of A is equal to sum from J equal 1 to N, where N is the size of the matrix, order of the matrix, of A1J, C1J, okay, which is A11, C11, plus A12, C12, plus A13, C13, plus dot, 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 up to C1N, no, I'm sorry, A1N, C1N. Okay. Now, here's why I said I don't want to write that. Because just in a page or two, we're going to say, well, it didn't have to be the first row. It could be any row. Or any column, okay? But I guess it was easier to write it this way to begin with and play around with. It doesn't matter which row or which column you use. Just pick a row, pick a column, and do it. Now, do you have to go through all the agony that we just did in getting the cofactors by doing first the minors and then the cofactors? No, actually, they're a lot easier than that most of the time. Okay, sorry. Now, in a 2x2 matrix, they mention here, the cofactors are merely the, if you're using the first row, the cofactors are the two numbers in the second row, okay? Well, not quite. The negative of the first member of the second row and the positive of the second member of the, So they say to do that, and I guess we can do it. If A was A11, A12, A21, A22, and you use the first row, okay, it just isn't even worth writing almost. You do A11 times the cofactor of A22 I'm sorry, A11, that's the first entry here, times the cofactor of A11, which would be A12, because when you wipe out the first row and first column, that's all that's left. So that would be A11, A22, plus A12 times the cofactor there, wipe out first row, second column, but because this is a negative entry here, plus minus A21, so that would be minus A12, A21. And sure enough, that is it. It's almost more of a pain to write than it is worth. When you use that definition to evaluate a determinant, you're expanding by the cofactors of the first row. And it says example 3 will demonstrate the procedure. I'm really tempted to give you a little bit of a shortcut. I'll give you a much better shortcut later, but I'll give you a little bit of one now. So here's this matrix A, which I think you've seen before. 0, 2, 1, 3, -1, 2, 4, 0, 1. And we're going to expand by the first row. But remember I said you could have used any row, any column. First row is just as good as any. And I'm going to shorten the process for you. Excuse me, just generally. Okay? We're using the first row and multiply it by the cofactor of the remaining. Okay. Now, here's how I start. First entry here is in a positive position, right? So it's going to be the positive this number times the determinant of down here. So I'm doing the sign change from the cofactor, I'm using it with the entry on the row. That to me makes more sense. The determinant down there is just the minor, and that's really easy to do. But why not put the sign with the position that determines that sign? That just makes more sense to me. But that first entry is a 0, so the first entry contributes nothing because it's 0 times whatever that determinant is. We don't care. Okay, so you move to the next entry. That's a 2. but that's in a negative position, so I'll put a negative 2 there. Okay? And then you can, if you need to, mentally wipe out that row and column, and then just multiply that by the determinant that's left, or the minor that's left. You don't need to worry with cofactor. You took care of the sign of the cofactor in the very first. So that would be 3 minus 8 is equal to a minus 5. So negative 2 times a minus 5. Okay? And then you'll have a plus 1, because that's the third entry in the top row. Okay? And if you need to do your little line there to indicate, that'll be 0 plus 4. Okay? So that'll be 10 plus 4 equal 14. There's the determinant of A. Okay? And they go through all the, well, what they did, they go back to example 2 where we already calculated the cofactors and just pull them in and use them. You could do them in your head just about the same way here, without flipping pages. Okay? So, now, then in the bottom part of the page, they say, although the determinant is defined as the expansion of the cofactors in the first row, it can be shown that the determinant can be evaluated by expanding any row or any column. Okay? So I want to do, they do 2 more of them for you. They do the second row, and they also do the first column. I'm going to be a little lazier than they, I think, and I'm going to do the first column. And the reason I'm going to do it, and I think you may have already got a hint of it, is pick the row or the column that has the most zeros in it. The first row had 1 0. No other row or column has more than 1 0. There are some without, like the second row has no zeros. Pick the one with the most zeros. It's like the first column also has that. So where I would begin there, the determinant of A, I left that off up here, I should have written that in, would be, let's do the first column here. So it's 0 times whatever, that's going to be 0. Okay? Then you're going to have a minus 3, because that's in a minus position, plus minus. Minus 3 times the determinant of what's left. 2 times 1 is 2, minus 0 is 2. Okay? Then a plus 4, because that's in the plus position here. Let me wipe out my line, and I'll wipe out that set and do this one up here. 4 minus a minus 1 would be 5. 4 times 5. Okay? So this would be a minus 6 plus 20 equal 14. Of course, same answer. Okay? And you better get the same answer. This time, just to keep up with the book, though I may be choosing different ones, I'm going to use the second column, okay? Because that has a 0 in it. So the determinant of A, using the second column, would be, you start here, that 2 is in the negative position, so that would be a minus 2 times the matrix that's left, the determinant of the matrix that's left, 3 minus 8 is negative 5, okay? And then we'll use this minus 1, but that's in a plus position, so that's going to stay a minus 1 times, now we'll wipe out row and column there, and that will be a 0 minus 4. Okay? What does this give us? Positive 10 plus 4 equal 14. That works just as well. Now the one other, I'll up the book by 1. They only did 2 more examples. I'll give 3. Just because it's that easy, we'll use the third row. Okay? Because that also has a 0 in it. So we're going to use that third row. I'm sorry, I shouldn't have wiped that out. And we're going to start with this 4. So the determinant of A from row 3. Okay? This was column 1. This was column 2. The one up here we did by row 1. Okay? By row 3, which also has a 0, we start with this, and that's in a positive position, so it's 4 times, wipe out this, and you have 4 plus 1 is 5. And then we go to this position. Okay? The 0 doesn't contribute a thing. This 1 here is in a plus position. It's going to be a plus 1. And we'll wipe out that column now too, and that gives us a minus 6. This will be 20 minus 6 equal 14. Every one gives you the same result. I didn't do the row 2 or column 3, which had 3 entries. They're still easy, but keep your, minimize your effort. Okay. So that leads to a theorem. This is theorem 3.1 on page 113. Okay. Let's see. Oh, I only got 3 minutes left, so let me get the theorem down and that'll be it. Again, A is going to be a square matrix. Got to be, otherwise you can't do the determinants. Of order n. Okay. Then the determinant of A is the summation from j equal 1 to n of any aij, cij, the product of those. Now, I don't do it this way. This is the technical definition of getting ahead of myself, ai1, ci1 plus ai2, ci2 plus ai3, I can't write, ci3 plus ... all the way up to ain times cin. Any row, pick the ith row, whichever one, anywhere from 1 to n, pick that row and then do the elements in that row times the cofactor, times that element's cofactor, plus the element of the second entry in that row, the ith row, and do like that. Or, the other way you can do it is, determinant of A is the summation from I equal 1 to n of aij, cij, but this time we pick the jth column, and we do a1j, c1j, plus a2j, c2j, plus a3j, c3j, plus ... up to and including a n j c n j. Okay? You just expand by that. Now, as I was saying telling you just a couple minutes ago, when expanding by cofactors, you do not need to find cofactors of 0 entries, because 0 times a cofactor is 0, so that's why you pick the row or the column containing the most zeros is usually the best choice for expansion by cofactors. And we are now out of time, so we'll begin next time with example 4, okay, on page 113. Sorry I had to take a break in the middle, but I'm feeling better now than I did before. Homework exercises here would then be any of the odds 1 through 11. They're all found in the back of the book. The answers are there. Our Calc Chat shows you worked out solutions for those odd number exercises. 13 or 15, all at Calc Chat. 17 should be at Calc Chat. And then any of the odds 19, certainly 19 through 25, they should all be at Calc Chat. And if you really feel aggressive, okay, I shouldn't use that term perhaps, you could try 27 through 31. Those are much bigger. Yeah. The first 19 to 25 are all 3 by 3s, with 23 being decimals in it, which still is doable. But 27 through 31 are 4 by 4s or greater. So you can try that. The next one we'll do in class, example 4, will be a 4 by 4. So if you want to wait until we do that one, you can. Okay. That pretty much is it for today and this week. I hope you have a good weekend, and certainly working on linear algebra should make it good. And I think both of you have your second test in hand, or at least Dawson does. I can't remember if Josh got it or not. I don't think you did. And the bad news there is neither one of you have turned in the first test, nor have you turned in a research paper. So I don't have any scores for either of you. Please get me something next week, please. Okay? So I'm going to put down the 2 absences here. All right.